This week we're going to start talking about the gases. Generally, when you think of states of matter, we know there's solids, liquids, and gases, but in our everyday life we tend to think more about the solids and liquids. We run across them all the time. I mean, this desk in front of me is solid, and I just had a glass of water. That's a liquid. But what about the gases? We know they're around, but they're clear, so we don't see them. But as a chemist, the gases are really probably the most interesting ones because they do stuff. Solids just sit here. Liquids just sit there. Gases, as you'll see, they actually do stuff. And you may have dealt with gas laws before. Part of that is because both chemists and physicists like to claim the gas laws. Physicists think the gas laws are physics. Chemists think the gas laws are chemistry. And so I know I learned about gas laws in about 4 different classes. So we're going to talk about the laws, which are equations in class. But here we're just going to start to talk about what gases are. So we know that what's around us, the atmosphere, is gas. You may have heard before that the vast majority of the air is nitrogen. Obviously, we breathe oxygen. There's about 21% of the air is oxygen. There's roughly 1% of argon. Of course, there's 0.032% of CO2, and hopefully that doesn't go up much more, of course. But everything after that, it's tiny, tiny, tiny amounts. But it's mostly nitrogen and oxygen, and then everything else makes up the rest. We're going to talk about a lot of different properties of gases, and one of them that sort of helps summarize all of them is density. And if we think of the density of different states of matter, we already know that gases have the lowest density, with in general solids being the most dense, then liquids, and then gases. Of course, water is one of our exceptions because ice cubes float. But if you look at our pictures here, you can go back and forth between whether solids or liquids are more dense. It kind of depends on what you're dealing with. But there is never going to be an example where a gas is more dense than a solid or a liquid. Gases are by far the least dense state of matter. So, just like our solids and our liquids, the gases are made up of atoms or molecules. If you just think of them as generic particles flying around. They're just flying around, and pretty much everything in the gas is empty space. The particles are really far spread apart. Pretty much everything is empty space. But those gases are moving really, really fast. An oxygen molecule moves at 980 miles an hour at room temperature. And we'll see how temperature changes that speed. But at room temperature, an oxygen molecule is moving 980 miles an hour. That is really, really fast. And when they're flying around, they don't really affect each other all that much. Okay? They're flying around just like the other molecules don't exist. And when they hit, they bounce off of each other. They don't stick, and we'll talk about this later, but it's what we call an inelastic collision, meaning there's no energy transfer. Imagine a pool ball bouncing off another one. When the cue ball hits the other ball, the cue ball bounces off just like the other ball didn't absorb any energy from it. So, if gas molecules move that fast, imagine I open a bottle of perfume on the other side of the room behind me. How long is it going to take for a molecule or anything moving 980 miles an hour to get from the back of the room to me? Not very fast. But you know from experience that if I open a bottle of perfume back there, I'm not going to immediately smell it. So why is that? I mean, it seems strange, right? But imagine a highway in the middle of the night, nobody else on the road. You can get anywhere you're going really fast. But what happens at rush hour? You hit other cars. Other cars get in your way. You can't get where you're trying to go. So those perfume molecules coming out of the bottle behind me, they run into other molecules on the way trying to get to me. And so they have to take detour after detour after detour after detour. And it takes them quite a while to actually get to me. By the time they get to me, they've moved, they've flown a whole lot further than directly from the back of the room to the front of the room. And another property of gases that you already know is that gases will expand to completely fill whatever container they're in. And you also know what temperature does to density of gases. You may not technically know this in a textbook sort of way, but through experience, you know what this does. When you heat gases, what do? They expand. You know that. But why do they do that? When you heat up gases, the molecules start moving faster. Temperature is a measure of kinetic energy. If you increase the temperature, you increase kinetic energy. Increased kinetic energy means you're moving faster. If you're moving faster, they're going to be flying a whole lot faster, and they're going to spread out. That's what causes a decrease in density when you heat a gas. Take the same amount of gas, you heat it, it expands. Density is mass over volume. If you increase the amount of volume, keeping the mass the same, your density is going to go down. So we're looking at this picture here. We have the same gas at a cold temperature and a warm temperature. Which one has the higher density? Remember, density is mass over volume. In each picture we have the same amount of volume. This one has 4 molecules, this one has 2. So this one's going to have more mass, so density is higher. The cool gas has the higher density. And this is exactly why hot air balloons rise. If you take the hot air balloon and you fill it full of hot air, the air in that balloon is a lower density than the air in the atmosphere around it. And just like putting a cork in water, the low density thing is going to float. If you put a cork at the bottom of a container of water and let go, it's going to float. If you fill a hot air balloon with low density air and untie the ropes, it's going to float. Another thing that you know about air and gases is effects on pressure. Think of your tire on your car. If we change the amount of air in your tire, we can change the amount of pressure in your tire. Here's a flat tire. Okay, imagine if we fix the flat, now we have to pump it back up. What happens to the pressure inside that tire when we add air? The pressure is going to go up, right? I know on my truck, my tires need to be 35 psi. If they're low, what do? I hook a pump up to them and I put more air in. Why is the pressure going up? I think we'll see that on another slide, but the pressure is going up because we're having more molecules, and the molecules are hitting the inside of the tire more often. What happens to density? Remember, density is mass over volume. Assuming this tire is inflated enough that it has its normal shape, when we add more air molecules, the volume isn't going to change, but we continue to add mass, so the density goes up. So the density is going up with the pressure. So imagine a balloon, and we know that if we add more air to the balloon is going to inflate. But why is that? Imagine those air molecules in the balloon flying around. They're flying around really fast, and occasionally they hit the inside of the balloon. When they do that, it's like a little punch. It's like punching out on the balloon. But there are a lot of molecules in this balloon. So there are, at any given time, there are a lot of molecules punching out in every little spot on the inside of this balloon, and so it causes it to expand. And the more air molecules you add to the balloon, the more molecules are hitting the inside of the balloon, so it makes it get bigger and bigger and bigger. So we can talk about pressure in terms of an equation. Pressure is force divided by area. Okay? And force is the amount of energy, or it's a physical term, it's force. You know, if you push with more force, you're going to get more effect, right? An area is the amount of space that force is applied on. So this is the type of equation you might have seen in physics. For gas particles, we have a different one. It's the force of the gas particles divided by the area of the container. That's how big the inside of the container is. And we know how this works. In this picture, we have a push pin between two fingers. If we push down on that push pin, which one's going to hurt? It's going to be the one with the pointy end of the pin. Both fingers actually have the same amount of force being applied to them. It's just this one has a much smaller area, so the pressure on this one is a lot higher. The same thing if we hit a nail. When we hit a nail the normal way, all of that force gets put on the tip of the nail. There's a very high amount of pressure that allows the nail to sink into the wood. If we were to do it the other way around, the same exact amount of force would get applied over this much larger area, and so we wouldn't have enough pressure to force the nail into the wood. So that's just a very quick primer on what it means to deal with gases, and we're going to talk a lot more about them, more about the theory behind the gases, and then we'll get into the gas laws, which are equations that allow us to figure out what the properties of the gases are going to be when we change things like temperature and volume. So I will see you in class.